Welcome, my name is Ron Kaufman. I'm the Element Chair for Interdisciplinary Curriculum at USD's Humanities Center. And I want to welcome you to this very special event in our semester's programming, the Knapp Lecture delivered today by our distinguished guest, Jeff Drazen, whom I can just barely see over the monitor. A little aside for a moment, in academia, there's this interesting sort of genealogical thing that people sometimes do, where if you work for a particular professor, when you get your doctorate or a master's degree under a particular professor, you are considered to be that person's academic child. With that framing in mind, Jeff is actually my academic little brother, in the sense that my much more intelligent, taller, and better looking little brother, which causes me no end of aggravation, because we did our doctorate degrees at different times, but in the same academic research lab. A little about Jeff and the reason why we're all here tonight. This is, as I mentioned, the Knapp Lecture. The Knapp Chair of Liberal Arts was established in 1995 by a generous endowment from the estate of Mary and Churchill Knapp, longtime supporters of the College of Arts and Sciences here at USD. The Knapp Chairs contribute to the vitality of the liberal arts in the college by interacting with students, collaborating with faculty, and presenting public lectures such as this one. Previous Knapp Chairs have included Kathy Cohen, Mark Edmondson, Linda Tuiwai-Smith, Alexander Nemirov, and Noam Chomsky. To introduce our current Knapp Chair, Jeff Drazen, please welcome the Chair of USD's Department of Biology, Dr. Sue Lowry.
Along with this genealogy, that would put me as some sort of a second cousin or something, because the same person was on my PhD thesis committee. So it's a real pleasure for me to welcome Jeff here tonight. He was one of the most enthusiastic undergraduates that I have ever taught, and I've been here for quite a while. So I've seen a lot of people come and go, and we're also lucky to have other people from his class here. He and Pat Early were a dynamic duo in the marine science and biology departments at the time, because at the time you had to have not just one degree to graduate, but two. And so he graduated with a degree in both biology and marine science. For those of you who maybe have organized field trips, they're sort of legendary. In fact, they convinced us to have an extra field trip for the class that they were taking with me. And Michelle Boudriat and I took extra students out on this extra field trip overnight, where we caught midwater fish and, with the bioluminescence and all sorts of wonderful things. And just to show how unusually gifted Jeff is, he commenced to make a field guide and a key to midwater fishes, because I told him that one didn't exist to my knowledge. And so they created one and put it together just because it needed to be done. So since this time, he's graduated and had an illustrious career. He went on to the Scripps Institution of Oceanography, where he got his PhD. He did a postdoc at the Monterey Bay Aquarium Research Institute. MBARI is famous for its deep sea biology, and he has subsequently been a professor and previous chair of the department at the University of Hawaii at Manoa. And tonight he's going to talk to, so normally he would be doing work on the basic biology of these wonderful fishes that live in the deep sea, but he's now been involved in some of the collection of baseline data and involving deep sea mining. And so he's going to be talking to us about this very timely topic tonight. Welcome, Jeff.
All right, well, Ron, Sue, thank you very much. It is really great to be back here at USD. So yeah, some of these fishes that I got interested in long ago are right here and right there, and those are some of the things that Sue was talking about that we convinced them to go out and catch. It was great. So I'm going to talk to you about deep sea mining this evening, and I figure that a number of you are already aware of what deep sea mining is, but some of you might not even know what the deep sea is. So I'm going to back up and talk about the habitat first, and then, which is a little foreign to a lot of people, and then move into mining. So this is a picture of the globe with Hawaii right in the middle where I teach, and you can see how extensive the ocean is. And I think everybody learns in grade school that 70% of the Earth is covered by the oceans, but most people don't realize that about 65% of the Earth is covered in really deep ocean, 200 meters or greater, which is what we typically define as the deep sea. And so this is actually, when you sum it all up, about 85% of the living space on our planet is the deep ocean. And this is a picture of it from off California, which I thought would be appropriate for today. So if you were to go just 100 miles offshore here, you would see this rat-tail fish and these little pink sea cucumbers on the seafloor. This is what the abyssal plain looks like 2.5 miles down. So the average depth of the ocean is indeed 4,000 meters. And if you want to put that in other units, it's 12,000 feet, or about 2.3 miles down. So it's very different than the ocean we're typically accustomed to visiting when we go surfing or diving or fishing, those kinds of things. The average depth of the ocean is incredibly great. And this environment is characterized by being very cold, dark, either pitch black or just barely lit, extremely high pressure. This fish right here on this screen is experiencing 400 times the pressure that you're experiencing in this room right now. And it's a very food-poor place because there's no sunlight. And without sunlight supporting the phytoplankton, the marine plants that are generating food, there's just not a lot to go around. So animals are adapted to this food-poor place. Now, I've described the deep sea as one big place, and it's not. It is a host of different habitats, just like you would find in North America, where there might be forests and deserts and things like that. In the deep ocean, there are plains, and there are canyons, and deep sea trenches, and underwater mountains, and it is an incredibly varied place. And in these habitats, life abounds. There are enough microbes and animals to constitute about half of the mass of life on the planet. And the diversity of these animals and other organisms is incredible and rivals systems that we typically associate as being high diversity, like coral reefs and tropical rainforests. And I think it's also true, and part of the reason why I'm talking to you about the deep sea generally right now, that the deep sea is the last frontier on our planet. You'll hear this from the internet. The surface of the moon is better mapped than the bottom of the ocean. And that's actually true. Our maps of the deep sea floor are pretty terrible in places. And we are working to do better. And there's a big project called Seabed 2030. And we hope to have the oceans mapped in just another 7 short years, which I don't know that they will make, but they're trying. It's been estimated that there are 1 million new species waiting to be discovered in the deep sea, and these aren't just little inconspicuous things like worms living in the mud. Here are a couple of new species that we have found off of Hawaii. This is a king crab. It was found just a few miles from the city of Honolulu, 1,500 meters of water, and this is about a 6-inch fish right here. This is Hawaii's first snailfish. It's a very common family of fishes, but this was the first one found in Hawaii. We described it just a few years ago, about a decade ago. So this is very much a last frontier, and I think we're still trying to figure out how our human society interacts with this environment and how we might be affecting this environment. Importantly, I think it's nearly impossible to visit the deep sea. It's dark. And you have to have specialized equipment, so it's out of everybody's sight, and so it's out of everybody's minds. And I'm hoping that by the end of this seminar this evening, it won't be as much out of yours. Our society is actually quite connected to the deep sea, but in ways that most people don't realize. So we have a host of natural products that come from the deep ocean. This picture is rather gruesome. This is a pile of whale bones on the deep sea floor. And a very enterprising scientist some decades ago realized that there were microbes living on those bones in the deep sea, which is very, very cold, and they were breaking down the fats in those bones. And they realized that they could take the genetic material from those microbes, clone that, and they could mass produce these enzymes, which are now in some of your laundry detergents. because now you can run your laundry on the cold setting and not have to wash your clothes on the hot setting, which takes more energy. The bottom right picture is of a coral garden in Hawaii, and there are a couple of studies now that show there are a vast array of bioactive compounds in deep water sponges and corals, and some of those are now being explored for arthritis treatments and anti-cancer drugs. And we also get seafood from the deep sea. I've picked a couple of species here. This is called a rat tail, but no one will eat a rat tail, so the market renamed them grenadiers. So if you see, this has happened many, many times. If you see grenadier, and I've seen it in Vaughn's supermarket here in San Diego, this is what you're eating. I actually saw it in the supermarket, I don't know, it was a visit 6 years ago, something like that. So we're eating these things. This is a species you frequently see in high-end restaurants. This is called the moonfish or the opa. You'll probably find that down at the Brigantine. This is also a deep-sea fish. And even those species that we don't think of as being deep sea are connected by food webs to the deep sea. So that's the opa, but tunas, swordfish, these animals that we like to eat are actually connected to a food web, the surface up here at the top, the deep sea down here, and they're consuming small fishes and squids, and those animals living in the open ocean, they have no place to hide. So during the middle of the day, they descend to the depths and they hide where it's dark. And these arrows are just reflecting this migration. At night, they come back to the surface to feed because there's more food up at the surface. And all of these top predators have adaptations it's an evolutionary arms race. So they have these adaptations to dive to depth, chasing all of those organisms. Swordfish dive to 1,200 meters. Big-eyed tuna, 600 meters. Leatherback sea turtles, 800 meters. We now know that most of the big fishes that live in the open ocean that we have really thought of as being shallow water animals actually regularly are making excursions into the deep ocean. And this also transports carbon. If you have all these organisms and all the plankton feeding in surface waters, which is basically taking in carbon in their food, and then they migrate to depth where they breathe during the day, they're taking carbon out of that earth or that sort of surface ocean atmosphere carbon pool and sequestering it at depth, which is helping us with climate change. So these are some of the ecosystem services that the deep sea provides. And I think this is a good slide to show you. The next time you sit down to a plate of sashimi or a poke bowl or something like that, remember you're just one step in the food web removed from this crazy viperfish right here. So a new potential connection to this deep ocean environment is deep sea mining. This is not an industry that has begun yet, but is set to begin very, very soon. And their mining companies are after three main types of ore deposits in the deep ocean. On the top left here, we have a hydrothermal vent. These are places typically between 1,000 and 3,000 meters deep where water is superheated, it's full of minerals, and it comes rocketing up out of the seafloor. And when it hits the cold ocean water, all of those metals and minerals, they precipitate. They form what you can kind of see here is this black smoke. And over thousands of years, they create deposits around them that are full of zinc and gold and silver and copper. On underwater mountains, typically between about 800 and 2,500 meters, and you can see this underwater mountain here with a lot of deep sea corals on it, over millions of years, a very different time scale, metals that are in the water glom onto, they precipitate to the rocks on the flanks of these seamounts, and they create these crusts, which can be quite thick, and those have cobalt, copper, manganese, and nickel in them. If you get even deeper onto the abyssal plains, which is illustrated over here, you'll find these black potato-sized things that almost look like rocks. And that is where these same metals that were precipitating out of seawater on a seamount, well, they start to attach to a grain of sand or a shark's tooth. And over millions of years, they grow into something about the size of my fist. And they contain those same metals: cobalt, copper, manganese, nickel. There's iron in there as well. Well, why do we care about all of these metals? We need to make batteries. This is all about the green transition. If you use a lithium-ion battery, and I'm certain all of you do because you've all got a cell phone, that includes lithium, but it also includes cobalt, manganese, nickel, copper, all of these battery metals. That's what all of the to-do is about with deep-sea mining. The terrestrial sources of these metals still exist. There are still decent deposits, but they exist in places that are becoming harder to access. For instance, the biggest cobalt mine in the world is in the Democratic Republic of Congo, and they use 10-year-old kids to dig it out of the ground by hand. So there are real humanitarian concerns. So how did all of this start? How did we even find out about these minerals on the deep sea floor? And it's interesting, it goes back to the Challenger expedition. This ship right here in the 1870s did an expedition for 4 years all the way around the world, and it was the birth of oceanography. It was the birth of sort of understanding the deep ocean as an ecosystem. And when they did this around the world expedition, they dredged in the Pacific Ocean, and up came these manganese nodules. And at the time, they really weren't sure what these things were, but that was the first discovery of them. There has been interest in them ever since. There was a period in the 1970s when they thought they would go mining, and then that kind of died down. But that interest has really come back in force in the last 15 years because the deep sea oil and gas industry now regularly drills for oil at 3,000 meters. And all the tech they use for that can be applied to deep sea mining of metals. And so the tech is available. That, in addition with the need to create batteries for the green transition. And here we are today with many licenses being filed on the high seas, and many countries exploring whether they have metals in their offshore environment. Now, I will emphasize that testing of equipment and exploration for resources is happening right now. No commercial scale mining has begun yet. And that's kind of nice because this provides us with the opportunity to come up with good management strategies for this endeavor. First thing to realize is that the scale of this potential deep sea mining is massive. This is a map showing Hawaii, San Diego up here, and all these colored polygons are licenses that exist today for deep sea mining. Those are 18 of the licenses globally. I'm just showing these in this region called the Clarion-Clipperton Zone. And if you superimpose these onto a map of the continental US, they're basically talking about strip mining an area from California all the way to Pennsylvania. It is massive. And it's also very much in our regional neighborhood. This map is quite a very optimistic map about where all the deep sea minerals might exist. So all these colors are where deep sea minerals might be. They're probably not in quantities that are actually mineable in most cases, but a couple of the areas of interest, this is Hawaii right here, and the prime crust zone, this is a portion of the seafloor to the west of Hawaii all the way to Guam, and it's part of the oldest oceanic plate in the world, and so those seamounts have had millions and millions of years for those crusts to form on top of them. So people want to mine over here. And another area, the one I'm going to talk really about today, is this Clarion-Clipperton Zone, this span of ocean between Hawaii and roughly San Diego, Central America. And that is a place on the abyssal seafloor where there are lots of manganese nodules. And importantly, those nodules have really high metal content to them. So they're very attractive for miners. The mining equipment has been built. Some of the devices are shown here. On the left, a company named Nautilus Minerals. They were going to mine sulfide deposits in Papua New Guinea. And you can see these giant vehicles. These are prototypes, so they're about half the size of what would be developed for commercial scale mining. And those are 2 people right there, just to give you scale. So they're every bit as large a device as you would see being used in a pit mine on land. They're massive. This vehicle over here is the one that the Japanese are using, their government agency JOGMEC, and this head can be changed out, but they have mined sulfide deposits within their own exclusive economic zone, and in 2020, they actually mined cobalt or metal crust off of a seamount. All test mining. These activities typically go on for a couple of days. This is a video that will show you the mining instrumentation by a company called the Metals Company. This test was conducted in the latter part of 2022, so a little less than a year ago. There's their tracked mining vehicle, and it's being deployed off of a surface ship. They have very good videographers. Gotta love a marketing team. So they're remotely controlling this crawler across the seafloor, and it has heads that slurp up all of the nodules and the mud, and then it's connected by these pipes to the surface ship. And once that ore and mud is collected, it's rocketed 2.5 miles up. It goes through this separator right here, and you have nodules. And actually, they're nodule fragments. They are little broken pieces of what used to be mostly about the size of my fist. So there you go. They collected several tons of nodules in late 2022. So how is all of this going to be managed? So this seems to be coming. The management is conducted by a UN-created body called the International Seabed Authority, and they were established by the United Nations Convention on the Law of the Sea, a treaty that most nations in the world have signed. Interestingly, the United States is not. And they have a dual mandate to promote mining for the common heritage of humankind and to ensure the effective protection of the marine environment. And a lot of people have claimed that that dual mandate is very hard for them to negotiate, just one entity, because these two goals at times can be at odds. Some maybe would argue at all times. The ISA has a goal of approving exploitation regulations. In other words, the regulatory framework under which someone can submit an application to mine, and they want this done by the end of 2025. So it's 2 years. They were supposed to have it done a couple of months ago, but they didn't have enough time, and so they punted and they gave themselves 2 more years. But this is going to happen. Companies can actually start to submit their applications very, very soon. So the important thing about all of this is that while this is regulations on the high seas, where a lot of the deep sea mineral resources exist, if you've signed the Convention on the Law of the Sea and you're party to this agreement, keep in mind the United States is not, but you have to ensure equal or better protection if you undergo mining in your own territorial waters. So whatever rules are composed by the International Seabed Authority may end up governing the industry even within states' territories, at least many states. So a lot is at stake for this process. So what are the environmental risks of all of this? So we know what they're after, we know how they're going to get it. Do we care? I mean, we certainly need metals for the green transition. What is the potential downside? This diagram here shows a collector vehicle, and it will enable me to sort of go through some of the potential environmental risks here. This is the collector vehicle, and I'm really going to focus on manganese nodule mining because that's where we think mining is going to start. They want to make electric car batteries, and these have the best metals for that. Here's the riser pipe, like you saw in the video, up to a surface ship, and then this is the discharge pipe where all the unwanted material goes. But if we just focus on the seafloor, they're going to remove all of those nodules, which lie right on the bottom, and the top layer, several inches of mud. And that's going to remove the nodules as a habitat for organisms, and it's going to kill most of the animals that live in the sediments themselves. It's going to crush them or actually suck them all the way up to the surface. We think, based on what mining companies tell us, that they're going to harvest about 300 to 600 square kilometers of seafloor habitat per year. So over the 15 years of an initial license, that's about 10,000 square kilometers. Now, it's not just these direct impacts of this giant tractor going across the seafloor. On the abyssal plain, the mud is incredibly fine. The water down there on the abyssal plain is super clear, some of the clearest in the world. And you're going to kick up a giant cloud of this fine mud, which is going to drift for tens of kilometers away from the site of mining and settle. And that's going to bury animals. And we've done studies on this, and it will kill those animals. So that's going to then expand the area of effect up to something on the order of 50,000 square kilometers over 15 years of operation. That's the size of the nation of Costa Rica, a place whose conservation we care quite a bit about. So this is huge, and that's one miner. There's 18 licenses in the CCZ right now for exploration. So the scale is massive. Should we care about what's down there? I clearly do, but the fauna that you find, that we have found, is incredibly diverse. Here are just some images, and I'll show you a video in a little bit, but we've got all kinds of crazy purple sea cucumbers, fishes, which are my personal favorite, shrimps, crustaceans. This anemone right here actually belongs to a whole new family of anemones, and its tentacles are 3 meters long. They're about 9, 10 feet long. It's just amazing. And a lot of these organisms live right on the nodules themselves. You can see this connected down here to this little rock-like structure. All of these sponges and corals and things live on the nodules directly. About half of the diversity that we observe from cameras actually needs the nodules. That's probably why this place is so incredibly diverse. When we've been to the CCZ, we find much higher diversity than if we were to explore the same depths right off California, or the same depths off of New Zealand. We've made all these comparisons. The North Atlantic, this place is always more diverse. It's because of the nodules. It adds another type of habitat, a solid bottom amidst all of the soft mud that organisms can attach to. It creates a lot more niches for organisms to inhabit. So, and it's important to keep in mind that these nodules take millennia to grow. So if they are removed, the animals that need them for habitat won't see them come back for millions of years. That's an evolutionary timescale. So there are real concerns with that. A number of studies have looked at the resiliency of these ecosystems to disturbance. So if we go ahead and we mine a patch, how soon will all the organisms come back? And this is a track from one such experiment. A dredge was pulled across the seafloor. You can see the nodules over here. And you can see all the crumbled sediment right there. Maybe some of you at the back can't quite see those details, but it looks quite fresh. Now, scientists went back 7 years after they made this disturbance. They took cores, they pushed them into this mud, and they counted all the small animals, worms and the like, that lived there, and they found they had only returned to 15% of the abundances that had been there before they pulled the dredge through. So 7 years, the system had not recovered. These test mining tracks look very, very fresh. And I'm just curious, does anybody want to take a stab at guessing how old this track is when this picture was taken? You guys can just, sorry, I'm a teacher, right? So I have to ask questions. This should be participatory. Anybody want to take a stab? You know it's at least 7 years old. Cora, what do you think? Yeah, you're getting there. It's higher. Anybody else? Anybody else? Yeah, very close. This is 26 years old. So this is not an ecosystem like many of those we typically encounter in our own neighborhoods where you can damage it and it bounces back quickly. This is certainly not your front lawn. If your high school son comes home and he accidentally drives across the lawn and makes a bunch of tire tracks, you know, those go away in a couple of months. This, we think now, from all the experiments, Most of the faunal groups here take at least 26 years to recover. That's our best data. We have a little more data. It's not very good, but it suggests at least 37 years. And if we model all the results, and I won't show you those models, but we think that full recovery of these systems may take 100 years, something on the order of 100 years. And the organisms that live on the nodules themselves will not recover because, again, that habitat is removed permanently over the evolutionary timescale of the existence of those species. So this is quite dire, but it has the implication that if you start mining in an area like the Clarion-Clipperton Zone, if those mining activities take 100 years to progress across that zone, the areas first mined won't have recovered by the time you get to the areas last mined. So we need to think about the entire area being impacted at the same time. There's a big cumulative effect of the activity. So how can we protect these places? So I'm showing you a map of all of the mining licenses in the light blue and tan colors, and then there are some green boxes here. And fortunately, the International Seabed Authority was great. And in addition to requiring all of the mining contractors to generate ecosystem baselines, you have to go out and study what's there before you engage in mining activities. But in addition, they said, let's create a whole bunch of no mining zones, which are all those green boxes. And they're big. They're 400 kilometers on a side. So they were put in place with very limited knowledge. There are 9 of the green ones. It's sort of like trying to create the national park system in the United States without ever having been to the United States. You need to protect some area, but you don't know exactly what to protect. And so they were not based on thin air. We knew that, for instance, there should be some over here closer to Central America, and this is 3,000 miles, so there probably should be some more over near Hawaii because it's highly unlikely that all the animals are the same across such a wide span. And we know where some of the underwater mountains are in these places. We should encompass some of those. Things of that nature, productivity gradients all went into designing these. So it was unfortunately then taken by the politicians and the miners, and you'll notice that all of these green boxes are on the outside of all the mining areas. And I'm going to show you a video in a moment of our visiting 3 of these and trying to assess what's in them for the first time. They were been created for years. But I'll just sort of circumvent a little bit of that and say that we had a big workshop a number of years ago, and we shared all of our data and consolidated it, and we told the International Seabed Authority, you haven't protected enough nodule habitat. And so they actually listened to that, which was great, and they created these red no mining zones. And this one is right over the United States claim, which is quite interesting, but which is not on the map because the ISA doesn't recognize it. And so that will hopefully protect a whole lot more of the types of habitats and organisms that exist in this region. So what I thought I would do now is just show you a bit of video of an expedition that we took to the Clarion-Clipperton Zone, so you get an idea of what it looks like, and you get a bit of what it's like to explore these places for the first time, some of these no mining zones. Is the audio okay? Okay.
Vast areas of the deep Pacific are targeted for seafloor mining. Yet these are some of the most poorly explored habitats on the planet. The life of the abyssal seafloor, depths of 5,000 meters or about 3 miles, is weird and wonderful. There are animals with novel adaptations, sailing sea cucumbers, predaceous sponges. Yet most of these species have never been collected and are new to science. One of our main project goals is to explore the biodiversity of this region, to understand how they will be impacted by mining activities, and in particular to assess how areas set aside from mining, protected from mining, are adequate to preserve the biodiversity of this vast region. Why do people care about mining the deep sea floor? Well, it's covered in some areas with black potato-sized structures that are full of valuable minerals, nickel, copper, cobalt, rare earth elements that we need to make cell phones. And the supplies of the minerals in these nodules are enormous, a world supply for many decades of many of these essential metals.
One important element of this project is to evaluate the extent to which communities on seamounts or at shallower depths within each no mining zone can serve as sources of larvae to recolonize communities on the abyssal plain. And so that's one of the important routes for reestablishment of these communities after mining. And so one aspect we've been doing is sampling larvae and also looking at connectivity and species overlap between communities, these distinct habitats.
That's the second time that animal had ever been seen before. It's called a squid worm.
At depths of 4,000 to 5,000 meters, or about 2 to 3 miles, the deep ocean is extremely difficult to sample. It's a very remote habitat. We're using a variety of state-of-the-art techniques, such as benthic landers and remotely operated vehicles.
A real technological workhorse of our project is the remotely operated vehicle Illume. This goes descends to the bottom of the ocean with video cameras and manipulators and collects the animals that we need to study, as well as the sediment samples that contain the diverse microbes.
We missed that animal.
The most numerous and diverse inhabitants of the deep sea are microorganisms, yet they're chronically difficult to study. The approach that we're taking for this project is to study their genetic blueprint in order to better understand some of the ways that they obtain energy and recycled material in the deep sea.
The remotely operated vehicle is a marvelous tool because it allows you to target individual organisms, slurp them up into a chamber undamaged, or pick up sea cucumbers very gently with its manipulator and drop it into a box. We're able to collect all kinds of animals that have never been collected before in this part of the ocean.
This is where the alien abduction stories come from, right here.
Although we're sampling microbes and taking lots of animal samples to look at what is there, what species are there, we're also trying to ask questions about what are the animals and the microbes actually doing in sediments. And for this, we're using seafloor landers, benthic chamber landers, and also what are called microprofiling landers. These allow us to measure respiration rates, see how much the animals and the microbes are breathing at the seafloor, and also allow us to track how much food they process at the seafloor that we can then compare to other areas and build up an idea of how the ecosystem is functioning.
Beam cameras are a very useful tool to sample the mobile top predators in these ecosystems. So here we have one of the most common animals in the deep sea, a rat-tail fish. They have long, tapering tails that some early scientists thought looked like a rat's tail. At the seamounts, we found swarms of eels, a species that we're not sure of just yet. These are animals that are akin to lions and cheetahs on the plains of Africa. But because these animals, such as rat tails and eels, because they're so mobile, oftentimes they avoid the ROVs. So the beta camera system gives us a tool to track them right in front of our instruments to senses them. So often with natural resource management, we end up chasing our tail. The activity starts, and then we come up with a plan for how to manage it and how to conserve the resource. This has happened with fisheries. It's happened with mining on land. very unusual here because these reserves have been set up before the deep sea mining has begun. So we hope through our research to evaluate whether these reserves are adequate preservation areas for the region.
Okay. All right. So that we had an outreach person with us on that cruise, which was marvelous, that we could make something like that. So that sort of shows you some of the environmental risks that may occur to the seafloor and gives you a bit of an idea of how we go and study these places and what the environment actually looks like. And a couple of years ago, I got very concerned because the mining companies were talking about sucking up all of these nodules and then taking all the mud and just dumping it into the water column above the seafloor. They weren't going to dump it at the surface because it would cause a muddy slick that you could see from space, but they were going to dump it deeper down. And so we wrote a paper. It was basically asking about, well, what's going to happen to the water column? That's all of the ocean between the surface and the seafloor, which hadn't really been studied before. And to show you what this place is like, we've got a video of some of our work. It's a very different fauna than what you just saw living on the seafloor. You've got hosts of these amazing jellies. You've got all kinds of fish and crustaceans and octopi that are not like the ones you observe down at the seafloor. And so it is a very unique biodiversity. That's a pelagic worm right there. These are ctenophores. And it's a very, very unique diversity. And this is the community of animals that help support all those fishes. They dive into these depths to feed, like tunas and swordfish. And these animals also connect the shallow water to the seafloor environment. So it's a really important environment with a lot of interesting diversity. It's got an enormous fish biomass. This is an incredible aggregation of fish in the deep midwaters. So this is what concerned me right here. You're sucking up all the nodules from the seafloor, and you bring it up to that ship, and this process by itself is going to use all kinds of pumps that are going to be really noisy, or they're talking about injecting compressed air at depth to create lift in these pipes. These are all really, really noisy things that may affect all kinds of organisms in those habitats. And then that sediment plume, the modeling that's been done suggests that one mining operator will discharge about 50,000 cubic meters of muddy seawater a day. A 20-foot shipping container, which you can see on the back of a freight train or on a big Matson shipping, a container ship, that's about 50 cubic meters of volume. So it's 1,000 of those a day of muddy seawater that can be discharged somewhere in here. There's zero regulation on where they discharge it. So some companies are suggesting they'll take it all the way back down to the bottom, where the cloud of mud was made by the collector. And some are talking about discharging it at 1,000 meters or something in that neighborhood. So we've got those plumes, and it's not just the mud. As you saw from the collector test video, those manganese nodules, which start out the size of my fist, end up like little marbles. And so all those surfaces of those metals breaking, a bunch of metal dissolves. And so you have these little symbols here supposed to represent dissolved metal ions. You're going to have a chemical plume in addition to the mud plume. So we think these plumes of mud will travel tens of kilometers away from the site of mining. One study is suggesting something on the order of 40 to 80 kilometers away over a period of about 30 days. So what might that do to the animals that live in the water column? Well, as I mentioned earlier, we have the noise effects. The mud may cause animals with gills all sorts of respiratory distress. It's going to clog their gills like the gills on a fish. And there's a host of small animals, plankton, like this copepod on the top. And this animal is called a larvation, and it builds this mucus house you can see in this video. these animals strain or pick out really small bits of food from the water, organic particles. And if we're going to dump a whole lot of mud into the system, that's going to clog all their filtering apparatus, and it's also going to make them have to sift through a whole lot of useless mud particles to get their food. And these animals are often the base of these midwater food webs. So mud may settle on the bells of all those beautiful jellies that I showed you in the video. That's probably going to provide them with some buoyancy issues. We have the issue of toxic metals. Another concern that we have in the water column that we didn't as much on the seafloor is a reduction in visual communication. This is a midwater spookfish. Look at those eyes. That tells you right there just how important vision is to some of the animals that live in these habitats. And that's because they're using bioluminescence. This is a dragonfish. You're looking at its belly, the bottom of an aquarium. This fish was caught and placed in a tank, and you can see all of the lights. And of course, it's freaking out, which is why it's lighting up right now. These animals use light to find mates, to lure prey to them, right? Everybody's seen Finding Nemo. Everybody knows what happens when they go down into the deep. They use light, they visually communicate to a great extent, and the muddy seawater is going to shorten the distances over which they can do that because you can't see through the mud. So that's going to cause mortality of organisms, migration, shifts in community composition. These are all potential effects. Unlike the seafloor, where we actually have experiments, we have no experiments in the water column. We don't yet know. These are just what we think may happen. We don't know how important any one of those individual effects could be. But if we take all of those individual effects and we integrate them, the possibility is they'll affect populations, and then if they affect populations, they could affect ecosystem services. And so what I want to just share with you are some of our thoughts about how this might affect fisheries and our seafood supply. So the animals that we're talking about for our seafood supply are things like swordfish and tuna, because they're diving into these deep midwaters where these mining companies may discharge all this mud. And the noise and the clouds of mud may cause them to move. They're very highly mobile animals. They're probably just going to leave the area. So that may alter their migration routes. But the smaller animals, whose gills are clogged, and the plankton who can't filter feed anymore, that may cause a reduction in the food supply to things like tuna. And then finally, something that I'm concerned about is that it could actually contaminate all of these small animals with metals, and those then would get into our seafood supply. So this is a figure. I'm only going to have a couple of data figures for those of you who are not scientists. This is mercury concentration on a log scale, and each one of these points is one of these fishes. And we looked at mercury concentration. This has nothing to do with mining. This was just in the central North Pacific. This bottom axis is how deep they feed, their average depth of diving. So this deep diving swordfish up here has over 10 times as much mercury in its tissues as the surface dwelling mahi-mahi over here. And for those of you who know about mercury contamination, the effects of size have already been constrained from this analysis. So this is showing that naturally, not related to mining at all, mercury enters these deep water food webs. There are microbes down there, and we don't know why. They take mercury, they methylate it, and it can enter these food webs. If this happens naturally for mercury, is it possible then that if they're discharging copper and cobalt and other metals, that there may also be microbes that can make these metals bioavailable, and they will enter these deep water food webs? We don't know, but it's possible. What we do know is the overlap between the industry of mining and the industry of open ocean fishing. So we take a look at all of these boxes here. These are regions that are managed by what's called a regional fisheries management organization. They manage tuna fisheries on the high seas. And we took a look at their catch distribution over a 10-year period. It started about 10 years ago now. And we wanted to see how much of it actually came from the license areas, in the water column above these mining licenses. What's the overlap? How much comes from where, the ISA is interested in letting miners operate? And so, we did this for all of the licenses all around the globe, which are all in these colored circles. And ignore the figure to the right for the moment. What we found is that there are moderate amounts of overlap, but where there's lots of area that is covered by mining licenses, quite a bit of fish currently comes from these regions, up to 12% of the fish. If you want to get into the details, that's why the figure is on the right. It depends on how far you assume the plumes of mud will extend and what species of tuna you're talking about. Yellowfin, skipjack, big eye. So it depends on the species. But that doesn't seem like a lot when you look at individual countries, particularly small Pacific Island countries. 20 to 60% of their catch actually comes from some of these mining regions. So it's going to have a disproportionate effect on certain countries. These industries overlap. Right now, there was just at the last meeting of the International Seabed Authority, one fishing interest showed up. But right now, these industries aren't talking to one another. So this is a problem. So how can we protect these midwater ecosystems? Well, I had mentioned that we had published a paper suggesting that people needed to be concerned about the water column, and the International Seabed Authority did listen. So just like they created new no mining zones, they also said, okay, if you're going to discharge your mud into the water column, you got to do a midwater baseline too. So not only do you need to understand how the ecosystem works on the seafloor, these mining contractors need to understand how the water column ecosystem works. So we started the first one, and it's where this circle is on the map right there. And our goal was to describe the communities from microbes to fish, from the surface to the seafloor. It was a lot. I would also argue, I'm just going to throw this in here, I think that we need to create a regulation which states where these companies can discharge all this mud and potential dissolved metals. And that's an argument perhaps for the Q&A afterwards, but I think it should be much deeper, and I think it should be specified in the rules. So we conducted a baseline, and it's in this area called Nori D right here. It's actually a 5-day drive straight south from San Diego, which is where we left from in 2021 in the middle of COVID. And we conducted the first midwater baseline, and we used a great diversity of tools, from autonomous vessels, remotely operated vehicles, nets, water collection devices to look at microbes and dissolved metals and things of that nature. And we were funded to conduct 2 cruises in spring and fall of 2021. This was the Metals Company, and they're the first one to call for such a baseline study, which was great. And they had 2 sites. They wanted to sample where they were going to test their collector vehicle, the video you saw earlier in the talk, and a reference area, which is about 100 nautical miles away. And they were discharging their unwanted mud at about 1,200 meters depth. And I'm not going to show you lots of results because we're still generating these as we got most of the most recent data last year. So I will just say that there was significant biomass and diversity of animals at 1,200 meters where they wanted to discharge mud. This was the biomass peak for this cute little pelagic octopi called Japatella. And there were a host of endemic zooplankton, jellies, and fishes. So a lot of people had suggested, oh, it's the water column. It's the same there as it is all the way on the other side of the Pacific Ocean. No, this is not true. There are quite a few animals. About 70% of the fishes are endemic just to the Eastern Pacific. And the water column is extraordinarily variable, much more so, I would argue, than the seafloor. This is a satellite picture showing production in the spring in April and then in October. And you can see all the green color, meaning there's lots of phytoplankton and there's lots of productivity there. This productivity propagated all the way down to 1,500 meters depth in its effects. We saw changes in the abundances of animals and the composition of the communities. It was strongly seasonally affected. And then we also discovered there was a lot of variation in space. The 2 places, even though they were only 100 nautical miles apart and we went out there thinking they would just be the same, they weren't. Both times we went, they were different. And then we had, if you look at this bottom right graphic, this is an image of sea surface height. This yellow blob is moving through our survey box. This is an anticyclonic eddy. This is a big rotational circulation feature, and it actually brings a packet of water from over off of Central America and brings it through our study area. So that affected the last week and a half of our sampling when we were there in the spring, and it made a difference. We can see it in the data. There's a different community of organisms. The problem with all of this is that we have the start of a baseline. And it's really important to note that you have to study an area for quite some time to get a good baseline. A good baseline is one where if you go back and they've begun mining and you see a change, you can tell whether that's natural change or whether that came from the mining activity. And right now, we cannot do that in this environment. Not for the water column. There are some places on the seafloor where I think we probably can. This brings me to this slide here, and I'm almost done, that we don't have enough data for effective management. I don't expect you to look at this big graph right here of all these boxes, but every column is a different area where they are proposing to mine, and every row is a type of data that we think we need to scientifically inform management of the activity. And the colors in there, the darkest greens, are where we think we have adequate knowledge. You'll see there's 2 spots. The light greens are where we have moderate amounts of knowledge, and the white areas are where we have no knowledge. And this comes from a survey of the literature and stakeholders, and you find that only 1.1% of all these boxes here have enough scientific knowledge to enable evidence-based management of the industry. 85% of the categories in the Clarion-Clipperton zone, which is this column right here on the left, the area I've been talking to you most about, only 85% of them are dominated by gaps or no knowledge. So we don't know enough. We often don't know what the seasonal variability is like for the system, or we don't know how high a metal concentration they can take before it becomes lethal. There's big gaps. So if you're trying to create rules about how to manage deep sea mining, you can't do that based on data. Not very well. So to sum this all up, we have a host of environmental risks. Destruction of unique habitats, nodules themselves, the loss of biodiversity, all those organisms that live on the nodules, alteration of ecosystem functions like the transport of carbon from the surface to depth, negative effects on commercially harvested fishes. This is still just, we think it's a risk, but we don't know how important it is. Contamination of seafood supplies, again, it's a bit of an unknown, but it's a potential risk. And we need to weigh that against our desire for battery metals to assist with this green transition. It's a tough choice. And I think that part of the reason why I'm coming and speaking to you, and I speak to other groups as well, is that right now most people don't know much about deep sea mining, and you've got a group of policymakers at the ISA that are making decisions about half the surface of the planet, all of the abyssal plains. So I would argue that it's really society that needs to decide under what circumstances could deep sea mining occur. But it's something we all need to consider. That's sort of where I'm going to end it. There's a lot of open questions, and I would just like to thank a lot of collaborators and colleagues, postdocs, students whose bits of data I have shown you today. There were a lot of funders that made our research into this arena possible, listed down here on the bottom. And I really would like to thank the USD Humanities Center and Sue Lowry, Michelle Boudria, Andy Terrell, who were my hosts for this really wonderful Knapp Chair position. And I'd like to thank Mary and Churchill Knapp for creating this visiting professorship situation and the seminar series. It's really great. And mostly, I just want to thank my USD professors and mentors. Many of you are right here in front of me now, and I hope that this was a little bit better than my senior thesis that I gave many years ago. Thank you very much.